Hi, welcome back. So I just wrote down two multipliers that I used for constraints 1 and 2, 1/2 for each. And I'll note that that works out to give you a bound of 17. Okay, and the reason why, again, is that the 4x1 plus 3x2 plus 4x3, well, that's greater or equal to any possible objective, right? So let's write out the objective again. It's 2x1 plus 3x2 plus 4x3. And of course, that's less than or equal to 4x1 plus 3x2 plus 4x3, which is less than or equal to 17 because of the combination of these two. 8 plus 9 is 17 there. Oh, I didn't write the 1/2 on each side here. Of course, you need to do that as well. Okay, so you can see that I got a better bound by using, in some sense, smaller multipliers. And let's generalize this process, okay? We're going to let y1 be the multiplier for constraint 1, and we'll let y2 be the multiplier for constraint 2. We want to keep the inequalities to be less than or equal to. So we'll keep the y1 and y2 non-negative. We also want to enforce this notion that the coefficients in front of the x1 variable are dominate the coefficient in the objective. So this 2 coefficient, let's think about this. So we want the coefficients, and once we get the result of this, so we want those to dominate the coefficients in the objective for the respective variables. So what do we want? So we want that if we take y1 and we're multiplying it by this first constraint, the first constraint being 3x1 plus 2x2 plus 5x3. And remember, that's going to be this less than or equal to y1 times 18, right? We want that, and then if we add y2 times this other constraint, which was 5x1 plus 4x2 plus 3x3. Remember, this is constraint 2. 5x1 plus, I keep forgetting, 4x2 plus 3x3. And that's less than or equal to y2 times 16. Note the non-negativity is important so that these inequalities don't change. If we add that up, and we see we have 3y1 plus 5y2, that's the coefficient now in front of x1, plus 2y1 plus 4y2, and that's the coefficient in front of x2, plus 5y1 plus 3y2, and that's the coefficient in y3, in x3, I mean. That's less than or equal to 18y1 plus 16y2. Well, what this all means, in order for this to be a true upper bound on the objective, remember the objective was 2x1 plus 3x2 plus 4x3. Remember, that's the objective here. So we want that this coefficient in front of x1, 3y1 plus 5y2, has to be greater or equal to 2, right? Because we want this to be an upper bound on this. So it must be an upper bound. So that has to be true. That's for the x1 coefficient. We want the 2y1 plus 4y2 to be an upper bound on 3. That's the x2 coefficient. And finally, we want that the 5y1 plus 3y2 to be greater or equal to 4. That's the x3 coefficient. And I'm not writing this very neatly, so let me try that again. And we want the best upper bound possible, so we want to minimize, right? The lowest upper bound possible would be minimizing this 18y1 plus 16y2. So what do we have? We have some linear constraints here and here. So I have these in red. We have a linear objective, and what we get out of it is this linear program. And this is what we call the dual of that linear program we presented. It's in a completely different space, different variables, but it is a linear program. And what we're going to find in general is that some really surprising facts here. Every linear program has a dual. For minimization linear programs, right, we talked about maximum. Any feasible solution gives an upper bound on the optimal value, and any dual LP gives the greatest lower bound possible. We can generalize the process we just went through to develop some mechanical rules to construct duals. And I will talk about how that's done. But for now, what I'd like you to focus on is how to take duals in this sort of more interesting and really the Lagrangian way. The Lagrangian understanding here is that y1 and y2 are also called Lagrange multipliers. And that's just to, if you can recall back to Calculus 3, you talked about those there. And you also talked about that, I believe, in Calculus 1 when you were solving some optimization problems. And there's some surprisingly deep results that have to do with what we call duality. Let's talk about some of these rules. To construct the dual linear program, we do the following. We rewrite the primal. The primal now is the original. It's another way of saying original. So that's another name for it. So all the variables are on the left-hand side and all the constants on the right-hand side. So if we had, for whatever reason, like x1 plus x2 is less than or equal to 5 plus x3, then we would rewrite this to x1 plus x2 minus x3 is less than or equal to 5. Okay, so all the variables on the left-hand side, the constant is 5 is on the right-hand side. You assign each primal constraint a corresponding dual variable. Not for non-negativities, though. Or non-positivity. Then you write down the dual objective function. The coefficient of a dual variable is the right-hand side coefficient of its corresponding primal. And then the dual objective sense is the opposite. So a max goes to a min goes to a max. And then you write the dual constraint corresponding to each primal variable. And you get that by looking at the coefficients and making sure that it dominates the coefficient in the objective in the appropriate way. If it's a min, it has to be less than or equal to. If it's a max, it has to be greater or equal to. And of course, you have to be aware of the sign of the dual variable. Okay. To get the correct sign, what we do is we write the Lagrangian inequalities. In general, if there are n variables and m constraints at the right-hand sides, b1 through bm, along with the coefficients, in a minimization problem, we want that the coefficients that we get out of this in the dual are less than or equal to. They're bound from above by the original primal ones. So remember, these are the primal coefficients. And in a max problem, of course, the domination means that the coefficients, the original ones, are less than or equal to the new coefficients. Okay, the signs are derived from the inequalities. You take the primal constraints to be true and then restrict the yi's according to that. Then they're determined by the first inequality. This sort of leads to a following mnemonic. You should verify this table to be true. Okay, it can help you to remember, but it's best to first verify the truth of this table. Okay. Now, I'm going to leave you with this dual, and why don't we construct it? Okay, so our first thing is we see that what the form is here. We have the right form. The right-hand sides are constants and the left-hand sides are all variables. I'm going to assign variables. This is y1, this is y2, and we're minimizing. Okay, and this will be y3. So we've talked about, in this case, we've talked about the inequalities. We haven't talked about equalities, but let's write out what we call the Lagrangian relationships, and then we'll see. Okay, so remember, we're multiplying on both sides. So it'll be y1 on both sides of this equation, and we get 3y1 plus 14y2. Actually, I'm going to write it in the way that we just saw it. So I'm going to write the primal coefficient, the primal first over here. 10x1 plus 9x2 minus 6x3. We're minimizing, which means we need this to be greater or equal to y1 times 2x1 minus x2 plus y2 times 5x1 plus 3x2 minus x3 plus y3 times x2 plus x3. Okay, I'm going to rewrite this from this line to this line. I'm going to gather x1, x2, and x3 coefficients. Okay, so I'm just rewriting the same thing where all the x1 coefficients are going to be, all the coefficients for x1 will be in the same form. Okay, so it'll be 2y1 plus 5y2 plus 0 times y3 because there's no x1 here. Okay, so that's all x1. It's very important you understand how I just got that. So if you don't, you should stop and go back and see, or pause the video and see how I got 2y1 and 5y2 as the coefficient for x1. Okay, I'm going to do the same thing for x2. So it's minus y1 plus 3y2 plus y3. That's x2 coefficient. Plus there is no coefficient for y1 with x3, but there is for y2, so it's minus y2 plus y3 is in front of x3. And I need that to be greater or equal to the right-hand sides, which was 3y1 plus 14y2 plus y3. Okay, so let's think about this. The y1 coefficient, for that to be, well, let's talk about, first of all, what the constraints are for the dual. The constraints for the dual are going to be that 10 has to be greater or equal to 2y1 plus 5y2. because x1 is non-negative, that means that that 10 just has to be greater or equal to, the 10x1 has to be greater or equal to the 3y1. The 9x2 is different. Okay, because x2 is non-positive, it actually means that this, in fact, let me write this like this, just so we have that same form. The non-positivity of x2 means that, in fact, we have to have minus y1 plus 3y2 plus y3 has to be greater or equal to 9. And that's because the x2, were it non-positive, flips the inequality because it's being multiplied on both sides, right? And so that flips the inequality. x3 is non-negative, so indeed it respects the inequality the same way that the x1 variable did, and we get that minus y2 plus y3 has to be less than or equal to minus 6. Okay, so those are the constraints. I'll note that the greater or equal to 3 means that we have here y1 is greater or equal to 0, because, again, we need now this inequality to be respected. So we need that this to here, this is going to be greater or equal to. This has to be less than or equal to, because, again, we have that the 14 here right now, I'm sorry, it's this inequality that's has to be respected. We see that this this y1 has to be greater or equal to 0, because otherwise this coefficient won't be respected here. It's greater or equal to 3. The 14 has to be greater or equal to, so this has to be less than or equal to 0. y3 is both the easiest one and perhaps the hardest to see. For the coefficient here to be satisfied, because this is equality, equal to 1, the y3 is actually just a free variable. Okay, so the overall program is going to be maximizing, getting the best lower bound possible, so the greatest lower bound possible. And it's subject to the constraints that I wrote down, 2y1 plus 5y2 less than or equal to 10, minus y1 plus 3y2 plus y3 is greater or equal to 9, and minus y2 plus y3 is less than or equal to minus 6, with y1 greater or equal to 0, y2 less than or equal to 0. And I'm not going to write it, but y3 is free, so we don't need to have, there's no constraint on the bounds. So as an exercise, you can try to take this dual and also look at your assessment. I have a couple questions there for you to help you practice this. And this will factor into assessment 4. There'll be an online portion